Hello, my name's Josh, and this is my submission for the first project for computational methods. Um, there's not much code here because it's not what that's just not what I found that it required. So let's just get right into it. Starting off with our just given values. Um, these were the first things. I don't think you can see my Google Chrome page, but these are the first things we were given. So a length of 2 meters of the beam, which we have. A load of newtons of 1,000. A yield strength of 250 megapascals. So we converted it to pascals to keep everything in SI. The modulus of elasticity we're given in gigapascals, so we converted it to pascals to keep everything in SI. The deflection max, which was given in millimeters, so we converted that to meters, and then the density in kilograms per meters cubed. Next, we were told the beam has a rectangular cross section with width b and height h. These dimensions can vary along the length of the beam, but for simplicity, we assume they are constant. Next is our stress calculation. So we calculate the max bending stress. Oh, I'm kind of skipping some things. Let me go through these first. I was just reading through the Canvas page. First, we create our boundary for our contour. Our base can go from this be 0.001 meters, which would be 1 millimeter to 500 millimeters, and our height of 1 millimeter. Same for the height with 100 instances. And then we have our basic storage matrices that you see in all contour plots, or all the stuff we've done, like starting earlier on. We have 4 different types of contours that we're plotting, so we have our 4 different matrices. All right, now to the loop and all these formulas. So here you can see it says stress calcs. Here was our formula that we were given with our moment of inertia subbed in. It's just on the Canvas page. So I kind of skipped over the sigma max equals mc divided by I because I just went straight to the 6p times L over base times height squared. Let me go back to my MATLAB screen. Yeah, so that's the sigma max calculation that we're given. And then I just went ahead and calculated the critical stress. Our yield strength is calculated using sigma y, which is our yield strength of the material, and sigma max. So if you subtract sigma y from sigma max, if it's less than 0, you're good. But if it's greater than 0, then you violate your yield strength limit. And same thing for buckling. Sigma max, it needs to be greater than your sigma critical, and if it's not, meaning this would be, or sorry, if your sigma max is greater than your sigma critical, if you're putting more stress than the beam can sustain, which means this would be greater than 0, or this is greater than this, your buckling limit is broken or violated. Same thing with deflection. We're given formula in Canvas, moment of inertia subbed in. We then calculated our deflection constraint for all these different instances. And if your delta is bigger than the max your delta can be, your material is broken or it deflects too much. Next is our weight calc, which we're just given its density times volume times gravity, which is just here. Base times height times width, and you have your different height and base, or base times height times length, and you have your different base and height values with your associated with your I and your J. And then plotting, here's our plot for our weight, and then here's our three constraint plots. You got your yield stress, your buckling, your deflection, and then labeling grid, just to make like the plot look good. So if I run it, here's what we get. So I'm gonna go ahead and I want to see what time I'm at first. All right, 6 minutes. I'm gonna first knock this down. As you can see with our plot, I don't know where it went. We don't need to be this high. We're not picking values this high because our lowest value is 378. So we're gonna try and stay on this contour here with 100 weight instances plotted. This is where we could probably get a little lower if we plotted more, but that's where we're at. So I'm going to cut this height down to about 0.05, and then we can get a more accurate look at the plot. Hold up. We'll go down to like 0.25. Because that kind of killed everything else in our thing. Okay, we can kind of get a better look at this. If we zoom in, you can see our 378 right here is about where we want to be. Let's go back. It's kind of hard to see there. Maybe it's just easier to see if I don't cut off the plot like that. Why is my mouse doing that? I don't know. As you can see, the contour we're going to be on, the lowest weight contour is about 378.95, about 379 newtons. So we're going to try and stay on this contour, but we don't want to go too far. We pick too thin of a base and too high of a height, then we break our constraints. So we want to stay on the right side of these constraints and above these constraints. So in this kind of area is where we want to go. If we go over here, we're done for it. And if we go over here, we break our constraints too. So we stay on this 378 contour, which is the smallest one we see with this amount of instances in this spacing. You can see we want to pick a height of around 0.15 meters, which is 150 millimeters, and a base of around, well, it says about right there. Or sorry, a base of around 150 millimeters, a height of around 16 millimeters, right? Yeah. And to increase stiffness, you can try and go over as far as you can without breaking the constraint. So maybe we might be able to optimize it a little more. Let's zoom in. If you go to like if you go to about 130 millimeter base with about a 20 ish millimeter height, you can probably uh, optimize it a bit more, get as close as to this green line as possible without crossing it. But yeah, you can also go farther over and make your height or your base super big and your height virtually nothing, right? But then you get closer to that. So I'd say it's safest to stay far away from both of them so you don't get close to that buckling, which would be this red line, or this deflection, which would be this green line. And what's interesting looking at these plots is that you can see yielding actually doesn't do much on this material because your material will deflect too much before you yield. So if you didn't make this deflection max so big, if you made it smaller than 5 millimeters, maybe like 2 millimeters, maybe the yielding would be more of a concern than deflection would be. But since you made this deflection 5 millimeters, the deflection max, it's way more of a concern than yielding is to us. And as you can see, the deflection kind of dies out once you get to this sort of base here, this big base, and the yielding much sooner. The buckling is more of an x-axis base sort of issue, whereas yielding and deflection are more of a y-axis kind of issue, height issue. And I think that's all. So optimal height and base, I'd say around. Let me run it again. I'd say around 150. Yeah, 150 millimeters. Around 150 millimeters for the base, and then a height of around 15-ish millimeters. 16 it says here is probably your this is the most optimal, but an optimal base and height for this problem. So I just saw that my my figure didn't wasn't visible when I was filming the first segment of this video. So I'm adding this part. So I hope you see this. Yeah, let me move this out the way. Basically just what I was saying, a good point to pick would be about 150 millimeter base or a 0.15 meter base and like a 16 millimeter height. This is really just to show my plot and finish off the rest of this video. Sorry if there's some confusion, but you can rewind and kind of see what I was talking about here with the stuff on the right fitting the constraints. If it's on this side, it fails because it doesn't meet the constraints that we were given. You can see the buckling along the x-axis, the deflection, and yielding along the y or the height. And you can see that the deflection is more is an easier constraint to violate than the yielding, probably because the deflection max bending is only 5 millimeters. All right. I hope you can see this. Thank you.